and welcome to video 3, Missing Angles. In this video we're just going to talk very quickly through an example where we need to calculate a missing angle, and I'm just going to mention a couple of common mistakes that come up in this area as well. So first of all, you notice that I've got a blank diagram over here, and I just want to show you some labelling again. Now let's say I call this theta. That would of course give us an opposite side over here and an adjacent side there. We need to recognise here though that if I call this angle theta, this is now our opposite side and this is now our adjacent side. But really importantly, you'll notice here that this is always our hypotenuse, because the hypotenuse has two key features. The first one being that it is always opposite the right angle, and the second being that it is always the longest side. So just be careful of that. Now you notice something else here, that I've called these angles theta. Theta is just a really common naming convention for angles when we go into trigonometry. Theta is one of the Greek alphabet letters. And when theta is used, sometimes we'll revert back to some other Greek alphabet letters, such as alpha, beta, gamma, and epsilon, for example. But you can call it whatever you like. You can call it A, B, X, Q. It's just a convention. So you'll see theta a lot, but it doesn't mean you have to use theta. So with that in mind, I'm going to go to the example and I'm going to use theta. You can see my unknown side was marked there. And in this case, again, I've got my SOHCAHTOA. I know my opposite and I know my adjacent. I don't know my hypotenuse, and I'm not trying to find my hypotenuse. So that means that I'll be using tan. Tan is opposite over adjacent and does not involve the hypotenuse. So I have tan theta is equal to 5 over 7, opposite over adjacent. A couple other little tips for you here. If you're using sine or cosine, because you'll be dealing with opposite or adjacent over the hypotenuse, and the hypotenuse is always the longest, sine and cosine should always be equal to a number value between -1 and 1, and nothing else. If you find that you've got sine theta equals 1.4, something has gone wrong, and your calculator will tell you that it won't work. So just be very careful of that. Now I go through and I need to separate my tan and the theta. So I'm going to write this down as theta is equal to tan inverse of 5 over 7. And when I put that into my calculator, it gives me an answer of 35.53 degrees. And I'm going to leave it as that. We'll go back and have a look at angles in terms of degrees, minutes and seconds at some stage, but for now, 35.53 degrees is perfectly appropriate. It's really important here that you note that I used tan and tan inverse as my opposite operations. You can't simply divide by tan, and I see that done a lot, so be very careful. We can't just divide by tan and have theta is equal to tan of 5 over 7 or some other weird and wonderful thing. Always, to remove the tan when the theta is inside the tan or the cosine or the sine, you have to use that tan inverse function. We get an angle of 35.53 degrees. We always take this angle back and check, is it reasonable? Now in this case, I've made a deliberately misleading diagram. You have to be very careful of these as well. 7 centimeters and 5 centimeters, and you look at that diagram, the 5 centimeters seems to be longer than the 7 centimeters. Not all diagrams will be correct. But I do note here that my angle of 35.53 is opposite the 5, and that means that because these two angles must add up to 90, as we already have 90 accounted for in a triangle, this is approximately 55 degrees opposite the 7. So yes, that makes sense, because a smaller angle should be opposite a smaller side. So there you have it. Just one simple example, how to unwrap an equation where you have a tan, sine or cosine. Make sure you follow the rules. Think about those tips I've given you and maybe start writing down that advice so that you don't make those errors in your work. All the best.